Okay, I think we should be good to continue at this point. So yeah, let's do that. And I think I'm going to hide my meeting controls and get rid of this. And yeah, let's continue. So we left off, I think, down here after the date time stuff, at the start of this section about aggregating data in Pandas by grouping. So essentially what we're going to do in this step, as I've already mentioned, is take our observations that might be several times a day or even several times an hour and reduce the frequency, group them together by the year and the month so that we can calculate things like an average monthly temperature. Now, this is going to introduce the group by approach in Pandas, which I hope you'll find to be quite useful. So the first thing we're going to have to do there is group the data together. So we'll kind of select all the data as from the same year and the same month. Then we'll calculate an average, and then we're going to store those values that we've calculated in a new data frame called monthly data, because our current data frame has the indexing such that basically we're using these observations that are multiple times a day or multiple times an hour. And so we can't fit in a monthly average very easily into the existing data frame rather, but we have to make a new data frame for that. Let's just take a quick look at what we're dealing with here. So again, we have 757,000 rows in our data frame that we're working with. And again, things look more or less like this. You can see a couple extra columns we've added here with the month and the date in the date time format. But otherwise, we have our temp C, which is going to be one of the main things we're interested in. The other thing we can see here is that for these observations with the year and the month, here we are in the second day of January of 1906 with these last two values here. First three are from the first day of January, second day of January is here. And you can see that the year and month hasn't changed between those. We can essentially take advantage of that because the year and month will be the same for every observation from the month of January in 1906. And we can group things on the basis of exactly that. That's the kind of benefit here for how we're going to do things. We'll start it out by typing grouped. This is our variable that we'll use for all of our groups that we're going to create, and it's data.groupBy. And then in here, we should give a column name. And in this case, we're going to say year_month, because then that will find everything that has the same year and month and put it together as a group. Let's go ahead and run that one. Yeah, it's also possible to sort of create combinations in other ways like what's shown here in the note, but we already have this year-month combo. If we take a look at the type of this data, it's already filled in here, so we can just run this cell. We see it's a Pandas group by data frame group by object, so a little bit different data format than we've dealt with previously. And if we look at the length of it, we can see there are 601 values in this case here. So what that means for us is that there are 601 months of the selection of years that we have because we've grouped everything by year and month. If you remember when we looked back at the unique years we had, I think there was something like 50. 50 times 12 would give you approximately, I guess, should be pretty much 600. So we're very close to having 50 years of data in the data set that we have here. If we look at the N unique in this case for year month, we get 601 back as well. So this is the number of unique values for the year and month in our data frame here. And so we should expect in this case, since we've grouped on the basis of year month, that these two numbers should be the same. Just a kind of nice way to check and make sure everything is working as expected. Now, what we could do at this point is print out our group keys. If you do this, there's a lot of them, which is why this was commented out to begin with, but it allows you to see, for instance, all of the years and months that we have. So like here's 1906 January, 1906 February, so on and so forth. Things are looking pretty good. Here we hit 1915 December, and then it jumps to 1979 October. So here's our data gap, and it's pretty significant. From there onward, it looks like we have pretty continuous observations. So in a sense, it's kind of good that we have a block that's missing. It's just a continuous block of missing data, but obviously we're missing quite a bit of information here between 1915 and 1979 for this particular station. But yeah, anyway, it's nice to see like here's all of our different unique months and years that we have. In order to access the data from one of the groups, we can define, for instance, a month and year that we're interested in. So let's say, for instance, if we say month equals, and let's call it 1906-01. So this is January from 1906. And if we make now a group one variable, we could say group one equals grouped. That's our the groups that we've created, .get underscore group. And then we give the key in this case, which is month. So that will assign everything that has that key to this variable called group one. Let's see what we have in group one. So I run this, and it looks like we have a data frame. And in this case, what you can see here is what looks very much like the head of our file from before. So here's our time, 1906-01-01, 6 a.m. So that's basically what we had at the start of the file before, but now the end of our group comes 1906, January 31st at 8 p.m. And that's the last observation. So we have 92 or 93 rows. So 92 is the maximum index, 93 rows for January 1906. So in other words, we have 93 observations from that month. So that's kind of nice because we have a data frame that comes out of this, which means we can do data frame stuff. We can, of course, check this. If we type of group one and run that, we can see that it's a Pandas data frame. And that's kind of a nice thing, yeah, because again, we already know how to calculate things like the mean value of a column in a data frame. We've done that before. That's not a problem for us. So we're going to put together then a sort of more efficient way to do this for multiple columns at once by defining here mean calls. So these are all the columns where we would maybe want to calculate what the mean value is. I'm not so sure calculating the mean wind direction has a lot of meaning to it, but we could do it. Mean speed and gust, sure, those make sense. And then temp F and temp C, sure, why not? Let's calculate those mean values as well. And so we could then make some kind of Pandas series, for example. If we said mean underscore values equals group one, so that's our month of January from 1906. We'll take the selection here of mean calls. So these are all the columns where we want to calculate the mean values, and then dot mean, just like that. So here is our selection, a single group out of our grouping that we did earlier. So these are all the observations from January 1906. Here's the selection of columns that we want to do something with. And then we just take the dot mean of that selection of columns, just like we would with a regular data frame. And if we then print out what is in mean underscore values, when we run this, you can now see a mean direction, mean speed. Apparently there were no observations of the wind gust, and then mean temperature in both Fahrenheit and Celsius. So that's pretty nice because that is very easy to take a single group and calculate things like the mean values. So if we were to group by year and month, as we have for all of the data that we have, then we just need to find a way to calculate the mean values for each one of the groups. And there we have it. We've aggregated our data. Let's go on to that next step here. So just like we did with the iter rows, we can iterate over the different groups that we have using a for loop. And very similarly, we had idx, comma, key, I think in the, in the case for iter rows, we can say here for key, comma, group, in grouped. Again, grouped was the group by object we created with all of the year and month data grouped together by year and month. We can then say print key, for instance here, and then first rows of data in this group.head. So the group here is going to be one of the groups, and then the key is going to be the key that's used to create that group. And again, we're going to break this after the first iteration here just to see how things work. So for key, comma, group, in grouped, we're going to print out the key and print out the group.head. Let's just run that one to see what we get. So for the first one in our loop here, our key is 1906-01. That makes sense. We grouped by 1906-01. And then this is the first 5 rows of the data in that group. This is something that we basically saw above here. If I scroll back up for a moment, when we looked at what we had in group 1, that was using this grouped get group for a given month. And essentially we're getting that same data when we print out what's in the group here for this iteration over the group. So we can see then very easily how you can start to go through the different groups and do things like some of the calculations we're looking at. Now we can move on to doing exactly that step here. We're going to add together a bunch of the things that we've basically come to in different pieces in the parts of the lesson that we've seen so far. So first, let's make an empty data frame called monthly underscore data. And we're going to say it's just equal to pd.data frame with nothing in it, just an empty data frame. We have our mean calls from before, dir, speed, gust, temp f, and temp c. We're going to iterate over the groups like we just did. So this is going to be for key, comma, group, in grouped. What are we going to do? We're going to calculate a mean temperature or mean values, right? So mean underscore values, if we're doing more than just the temperature. Mean values equals group. And then we take the mean calls, the mean columns. So that's what we've defined above here. Same thing that we just did a second ago. Dot mean, just like that. So just as a reminder, that's basically what we were doing up here just a moment ago, where we did the mean calls and calculated the mean values for those columns from one group. Now we've seen how to iterate over the different groups, and we're going to now do the same thing where we calculate the mean values for each group as we iterate through this set of groups that we're dealing with. Then what we need to do is we'll create a new key for this year and month for the mean values. I'll show you in just a second. Year underscore month equals key. So you remember, again, sorry to kind of scroll back and forth a bunch here, but when we printed out our key, we had this text here. That was the year and month. It was the same thing that we had in the year month column previously in our data frame called data. Now, when we printed out these mean values, there was no, well, actually, I guess the mean values was calculated here. There was no key that was given here for the year and month to kind of link that to what these values come from. So now we're adding in our year and month as an additional thing in our mean values series. So mean values before had the mean for the direction, speed, gust, temp f, and temp c. Now we're going to add in another value there that's going to have the year and month for those values. And then we're simply going to add that to our data frame. So we'll say monthly underscore data equals monthly underscore data dot append and mean underscore values. So that's our data series that we have, comma, ignore index equals true. So what do we expect to see? First off, we're going to create an empty data frame called monthly data. Then we have these columns where we're going to calculate the mean values. We have a loop that's going to take us through each group. So for each month and year, we're going to calculate the mean values for the direction, speed, gust, temperature F, temperature C. Then we're going to add in what year and month it is to the list of those mean calculations. And then we're going to add that to our data frame. And let's see what happens when we run that. So it takes a moment, of course, but it's already done. And if we print out our monthly data, what we can see here is we now have a data frame. It's actually, I don't even need to print that. I'm just going to type monthly data so it looks a little bit nicer. That starts at 0, goes to 600. So there's our 601 rows. That's our 601 unique months and years. And for each year and month, we now have an average temperature in Fahrenheit, temperature in Celsius, and wind direction and wind speed. Cool. So we have now basically taken our observations from multiple times a day or multiple times an hour and condensed those down to being a monthly average value. Of course, we could do the same thing for all groups at once. And for all columns if we wanted to by just doing grouped dot mean. And if you run that, it will then take all the groups and calculate the mean values for all of the columns. But that's not necessarily always how you want to do things. But you get very similar results in this way, that you have 601 rows and 11 columns. Okay, now, our last remaining task is to try and detect the warm months, the warm Aprils, and to have a look at those. And this will take us just a couple steps to get there. So first off, we can start out by choosing the month of April. So in this case, our Aprils are going to be the case where we have data, in which case the data month value. So you'll remember if we did the check your understanding that we had this thing where we figured out which month it was, and it should be exactly equal to 04 as a character string to be the month of April. So those are all of the Aprils. So any data where the month is equal to 04 will be stored in a data frame here called Aprils. Now, the next step I've just left already filled in for you, and that is to take a subset of the columns that we are interested in. So here we have data, and then we have April's station number, temp F, temp C, and year month as the only things we're going to grab from here. That way we'll be able to group by the year and month as we just saw earlier. So we're basically ignoring all the months except April and doing very similar thing to what we just did. In this case, our grouped will be Aprils.groupBy. And then we say by equals year underscore month, just like that. Okay, so that's going to group all of the April observations by year and month. I think maybe just for the sake of clarity, I'll add another cell here just for a second and just show you what's in April's as the data frame. So what you can see here is only the observations for the month of April. So starting April 1906, going to April of 2019. So that's only what we have is the same well, I guess by this point, we've already reduced which columns we're dealing with, but only those columns for those months of April. We've now grouped everything by year and month. So that means that essentially everything that has the same character string for the year and month. So all of the April observations from 1906 will be grouped together and so on. And we can then very easily at this point, since we've already stripped away the columns we don't care about, do things like monthly mean equals grouped dot mean. So remember that with the group dot mean, you can take the mean value of all of the grouped values at once. And if we look at monthly mean dot head at this point, I guess I should run this cell first to do the monthly mean calculation. And if we look at what that produces, we now get for 1906 in the month of April, the station number is never going to change, but then we have a mean temperature and a mean temperature in Fahrenheit and a mean temperature in Celsius. I do understand that this might be a little bit confusing at this point about how all these things are happening. We'll work through this in the exercise again this week, so you'll have a chance to see it then. But basically, we're just combining the observations from those months. And since we have only the columns we care about, we're able to just do this group.mean as a faster way to get the mean values for these particular subset of columns. And then finally, we can do a sorting step where we sort by the temperature to figure out which months are the warmest in which years. So we could take our monthly mean dot sort values. So this will allow us to rearrange and sort things by, in this case, we'll go with temp C. Temp F would be the same, but let's just use temp C. And then ascending equals false. So we want this to be in descending order, so the warmest months at the top, and then dot head, so we only get the first, let's say 10. Okay, so monthly mean dot sort values by what? By temperature, ascending false, and dot head 10. Remember, we're working at the one station here from Tampere-Pirkkala, and in this situation, what we can see is that the warmest temperature, the warmest month on record, is indeed 2019 April. So we have at least one station that plays along with this idea that the month of April in 2019 was the warmest. Then you've got to go back to 1990 and 1989 to find the next two warmest. And then it's 2011, 2004, 2002, 1983, 2008. So it's a bit kind of scattered, but what we can see clearly here is that the warmest of all of them was April of 2019, and it's actually 5.8 degrees. Mean temperature is a bit higher significantly than some of the others. So it's the warmest. Now the next step here would be to take this same thing and repeat it for all of the stations. And this is kind of mostly just to show you that this is possible. This is not something that I think we're going to be using in the exercise, so don't worry too much about anything other than maybe just running some of these cells and following along with what we're doing. It's just a fun demonstration at this point. So here we have, we're going to read in the data file again, only take a selection of the columns. So we're going to get rid of like anything that we've changed in the data file. So this is kind of like start to finish what you would do to read in the data, convert the temperatures, aggregate things by the year and month, and then do this for multiple stations at the same time. So it's combining a lot of the steps that we've already seen in other parts of the lesson. We first read in the data file, then we rename the columns as we would like here. So we've got some new names, then we do the data.rename. We can print out the station number and the number of observations just so we can see that on the screen. Then we can make a column for temp C and fill in the values with our function far to Celsius as we did before. Then we convert our time from this sort of numerical value to a character string, and we can create a month and year and make those as two separate things in this particular instance. Then anytime the month is equal to 4, we can assign that to be our April, take a subset of the columns that we want to work with, group them, calculate the mean values, and then print that monthly mean ascending false out to the screen so we can see which months are the warmest. So if I run this cell, it's going to read in the data file and do all of those steps. What you see printed out to the screen is the station number, number of observations, and then here, year 2019, month 4, as having the warmest temperature on record. Again, this is for the Tampere-Pirkkala station. At this point, we need one more piece to be able to do this to a bunch of data files at once. And that is to use the glob or globe. I don't know how it's pronounced. Glob sounds kind of not so nice in English, so let's call it globe. This function, as part of a module called globe, allows us to essentially expand a sort of search for files in a given directory, not directory, given directory. So for example, if we import the globe module, we can then make a file list that's equal to globe.globe. And then this is a raw character string, so it starts with the R. Anything that's in a directory called data that starts with a 0 and then star and ends in txt will go into this file list. So essentially it allows us to use things like a wildcard, which is this star character, to find any file that's in the directory called data, starts with a 0 and ends in txt, and add that to our list of files. The reason we want to put the 0 here is because there's also a couple other text files that start with like a 6 that are some of the metadata, not actually a data file for our what we're working with here. So this allows us to kind of search for anything that matches this character string in the file system. So we're going to find all the data files that start with a 0. Let's just take a quick look over here in data, and you can see all of our data files here. These 15 should all be found by globe when we use it like we've instructed here. That's what we hope to see at least. If we look at the number of files in the list, we see there are 15. If you print out the file list that came from globe, you see now data slash this, data slash that, all of the different file names that we have here. So for FP in file list, if we just run that and print them out, these are our different data files, which means we can use the same for FP in file list to iterate over all of our different data files and do all the steps that were done up here, which is essentially the set of steps to process our data. So we take what we had above and just put it inside a for loop that goes for FP in file list. Every time we hear at the start, we'll begin by reading in a data file. It will take FP from one of the files in the list, read it in, and do all of the operations to calculate what the temperatures are for the month of April and sort them. And now if I run this, and we wait a little bit, we'll start seeing output written to the screen for all of the different stations. So again, you can see the station number, number of observations, and then the month of April that was the warmest on record. So here we have 1937 with a temperature of 6.27 Celsius for this station. I don't know what the station name is. We'd have to look at one of the metadata files. That looks to me like a bit of an outlier, given the others are more like around 4 degrees. So it might be a little bit suspicious about whether this station has some spurious data. But otherwise, 2019 is the second warmest there. The next station, we've got 2019 as the second warmest, and it's the warmest station here. It's number 4 at this station, number 3 at this one. 2019 is not on the list for this location, but then it's the warmest here, and so on and so forth. So you can scroll through, and what you can see is that in many places, 2019 was in fact the warmest year on record. It does look like maybe 1937 wasn't just one bad station, because there's also very warm temperatures in another location. But essentially, this has allowed us to now process a huge number of observations. You can see for each one of them, there's like, here's almost 1 million, or well, 930,000, getting there. 200,000 observations for this station, 750,000, 843,000. So there's a lot of observations of temperatures, and we've very efficiently now processed a huge amount of data for the sake of this lesson and this exercise. You'll be doing things similar to this in the exercise for this week. And mostly we just wanted to say, like, here's really what you can do with Pandas, is you can do these kind of pretty efficient and big scale data analysis things, just putting things together piece by piece into a kind of framework or a workflow that allows you to do the analysis of many, many data files at one time. So we could take, essentially what we've done here, we could take all of the European weather stations and then do the same kind of operation for hundreds or thousands of stations using the same code, essentially, as long as we put the data files into a format where we can, do something like use globe to loop over them. There's no matter whether there's 1 or 1,000 data files, the same workflow should work that way if they all have the same data format. So, any questions at this point? As I ran the data, my kernel announced that it had died. Yeah, that can happen. It should be the case in the CSC notebooks that you shouldn't run out of memory, but it's possible in some cases that you could. And if you were wanting to try and do this, you could always just go here to kernel and just restart kernel. And I'm going to restart the kernel and clear all outputs. So that's going to kind of reset everything. This last set of steps, as long as you go here to the step where you import, well, I guess at the very top, you've got to import Pandas. So if I was to go back up here to below where we found the data, so import Pandas at the beginning, and then scroll back down to the bottom where we imported globe and created our file list. Got to do that again, which is underneath here. So import globe, make the file list, and then I should be able to run this last cell here. So if you restart your kernel, you should be able to, oops, I guess I got to define the far to Celsius function as well. So I missed that one. And that's somewhere here. Now I should be able to run this last cell once again and get all of the same observations. So if your kernel died, you can restart, and you will have to import Pandas. You'll have to redefine the far to Celsius function and then do the globe stuff to create the file list once again. But yeah, if there aren't any questions otherwise at this point, I think it's probably wise for us to move forward. And for that, we're going to have one more little thing that I'm going to cover, and then Håvard will take over to talk about assertions and debugging. So I'm going to go back here to the notebooks in the file browser and open up the notebook called errors.ipynb. I'll just go through this sort of quickly. The point of the lesson here is essentially just to help you in interpreting error messages and reading them to try to understand what went wrong in your code. So here we have an example of wind speeds reported in kilometers per hour that we would like to convert to meters per second, because meters per second is what's used locally for wind speed. In Canada, where I lived a while ago now, they did wind speed in kilometers per hour. So again, it's one of these things where, like, maybe I'm familiar with that and I want a function to, or some way to convert my wind speeds from kilometers to meters per second. So here we have an example. And if you run this cell, everything's already typed in there. What you'll see when you run it is a syntax error that comes up. And the whole point is that when you see this error message, you shouldn't just like kind of shut down mentally and say, oh no, my code's broken, I don't know what to do. These error messages are here specifically to try to help you figure out what's wrong with the code. And so the syntax error in this case, this is not always necessarily that obvious. EOL, while scanning string literal, doesn't necessarily tell you very clearly what's gone wrong. EOL is end of line. So what you can see here, though, is that if you look, you have a syntax error, which means there's something wrong with the way that, something you've typed in here. So you have some kind of problem in the code. And oftentimes it means like you're missing a quotation mark or you're missing a parenthesis or something like that. And if we take a look at this, we could say, oh, yes, it is in fact missing a quotation mark here at the end. In fact, it indicates here with this little caret, sort of upside down V character, that it hit the end of the line and it says there's a problem somewhere near here because it should have had this other quotation mark. If I fix that and run the code again, everything is fine. So the syntax error in this case, it shows us the type of error, tells us where it occurred on line 4. And so if we look in our cell, 1, 2, 3, 4, yes, this is on line 4. And it tries to give us more information about what's gone wrong. Sometimes that information is very clear, sometimes it's not. And then it tries with this little upside down V to indicate where on the line it thinks the error has occurred. There's another example here. So now we've defined a function to convert our wind speed, and it should return the wind speed times 1,000 divided by 3,600. That will convert from kilometers an hour to meters per second. If I run this example, I get a different error message, in this case, a type error, and they get a traceback, which we didn't see before. The traceback occurs when there is an error that occurs at a certain point in a cell, but it's actually occurred somewhere else in the code. And the type error itself is where the problem lies. So what we can see, for instance, in this case, is that it finds on line 5 that there's a problem. It tries to do this wind speed meters per second by running this function called convert wind speed, and then it's taking a wind speed in kilometers. And it tries to do that and says, I can't, because when I go in here to actually line 2, where the function is defined, where it tries to do this calculation, it encounters a type error, and it says unsupported operands for division. So you can't divide a string by an integer. So in this case, the type error is telling us a little bit more information, saying I can't divide a character string by an integer. And if we look here, the value that's passed for speed comes into the function is this wind speed km. That's when we call the function, what we pass in. And sure enough, wind speed km here was written as a character string, and it's expected to be a numerical value. So if you fix that, then you run it and everything is good again. So I would encourage you to have a look at this. I'm not going to go through it in much more detail at this point, other than to say that there's different common error messages that are spelled out here. So there's index errors, there's name errors, indentation errors, type errors, and things of that nature, all of which you can kind of just see. If you run these cells, you'll get the examples of these different kind of error messages, and you'll see what they look like and what kind of information they give you. And there's some more information you can find about other kinds of error messages in Python that's on the Python documentation page, as well as some other lessons that you might find useful about this topic. And I finally wanted to note that Python 3.10 was just released last week, I think. And one of the improvements in Python 3.10 is the error messages. So if I just click on this link here, and you can do the same thing here, you'll find that what was previously a syntax error that looked like this, where it was trying to run this code here and encountered a syntax error, now has a bit more of a clear error tracing. So it now shows you in this file, example.py, this open kind of curly brace, so you can see an open one here, was never closed. So the error messaging in Python 3.10 has been improved with the idea that it wants to make it easier for you to track down what these error messages are. So instead of just something like invalid syntax pointing to this equal sign, which might be rather confusing, you look at that and you say like, this doesn't seem like a problem in syntax. Some variable equals some function. What's the issue? But actually the error comes up in this case because of something that was above that. And so now in Python 3.10, the error messages have been improved. And so you can have a look there. And we won't be using Python 3.10 because our environment would need to be updated at this point. And there might be some things that break with Python 3.10, but it is out there. And if you're installing it if you're going to install Python on your own computer, you might think about possibly installing Python 3.10. Okay, I think at this point I should let Håvard take over for a little bit to talk about the good coding practice and debugging stuff for this week. So I am going to stop sharing my screen.
All right, then I'll start sharing mine. And yes, so I'll go through the good coding practices for this week and also briefly touch upon debugging of your code. So this week's good coding practices can be found in the notebooks here under GCP 5 assertions.
Håvard, could you zoom in just a little bit?
Yeah,
on your screen?
I can make things bigger here.
That's great, thanks.
There we go. All right, and I'll just close the panel so we can see more. Okay, so assertions. Here this week we introduced the concept of defensive programming. So, which is for us to, or within assertions and error messaging, making sure that the code doesn't do anything wrong when you run it in short terms. So assertions is something that we use mainly in when we are defining functions, and they are a way to assert or make sure that the values and variables that are being used in our functions are within the limits that we want them to be, or within a certain type, and so on. So I'll continue with the example of converting wind speeds that we saw before. So if we start here, we have a simple function that converts speed from kilometers per hour to meters per second. So our function convert kph ms takes one variable, speed, and converts that from kilometers per hour to meters per second. And it's just a simple simple conversion where it times the given speed with the value that turns it into meters per second. And if we run this, it does what it tells us it's supposed to. It converts the speed, and it seems fine. But that is because we gave it, or it works fine for this instance, but we're not sure that it works for every instance of different values that we give the function. So for example, if we when we're measuring or when we're converting the wind speed, it is a measure of magnitude. So for example, negative values of wind speed doesn't make sense. So our function should also make sure that, or account for that. So for example, if we, in this example, write assert, and then that starts our assertion, and then speed, the variable that is given to the function, and here larger than 0. Then our function first checks that is the given variable speed, is that larger or equal to 0? And then if we run this, it does, because the given variable or value was 9, so that works fine. But if we give it a negative value of here -27, and run this cell, then we see we get an error message. And this type of error message is an assertion error. And as you can see here, it is on this line 3 that we created in our function, which is assert. So this is good. We have gotten an assertion error where the function didn't run when it on a negative value, because that wouldn't make sense. But we can also pass on more information when we create the assertion. So if we just ran this and it doesn't give us enough information about what was actually wrong and how can we fix that. So the way we can provide that information in the assertion is here when we create the assertion, after the what we want to assert, we write a comma and then a string value of the information that we want to pass on. So here again, if we run this with the pass it a negative number, then we get an assertion error again, but here it states wind speed values must be positive or 0. So that gives us some more information about what we did wrong, and then we can understand what we need to do to make it work. Yeah, so that is the general way that assertions work. You write assert and then some tests on the variables, and then the error message that you want to display if that assertion doesn't pass. So I can give some more examples here. We have some examples with multiple assertions, so we can do more than one assertion at a time. So here in the same function, we first assert what type the value we passed the variable or passed the function is, and then after that pass or assert the value of the speed. So here, if we then pass wind speed as a string, the dog, then we get an assertion on the type speed here. So and this is something you could do, but also as you saw that Dave went through, the type error is already one type of error that is created. So so this assertion of the type of the variable is kind of unnecessary, because we also already have the type error assertions that exist in Python. Yeah, so a better example of multiple assertions would be, in this case, asserting the value of the speed, and then first asserting that the value passed is positive or 0, and then after that asserting if the speed is smaller than 408, which is the fastest wind speed ever measured. So if we run this with the speed of 409 kilometers per hour, then we get first we get the type error that you saw. So even though we didn't have the assert type, which type speed was, we get the type error because we passed it the string 409 as a string value. So if we remove that and run it again as with 409 as a number, we get the assertion error. So this is just an example to show you how to create assertions that provides the correct information or the most usable information when creating functions. Yeah, so you can also read more about assertions on the link here, but then I'll open the debugging notebook for this week to give you some examples of how to debug your code. So when your code doesn't work, how can you fix it, and what kind of method can you use to do that? So debugging can be quite time consuming. So we want to give you a few pointers on how to do that. So our general recommendations for debugging is to first test your code with known outputs. So doing tests where you know what the answers will be, or you know what you expect and what it's supposed to be, so that you can actually check whether that is correct, the output you are getting. And then the second recommendation is to make your code crash quickly and regularly. So, and that might sound a bit weird, but as we have started working with larger data sets, the main thought is that you want to make your code crash as quickly as possible if there are errors, so that you don't start running a cell and it takes 20 minutes to run, and then after 20 minutes you realize, there was an error, I need to fix that and run the whole cell again. But rather make the code crash as quickly as possible, so that you don't waste time in that manner. And then the last general recommendation is to make small changes and track them often, and in a way just using GitHub actively, and see small changes every time, so it's easier to see when you have made the errors in your code and are able to go back and track when it happened and find the errors. So in the notebook, there is some examples of these 3 recommendations that you can read, and I recommend you to do so. But I also wanted to just have a little bit of time to use to show you the debugger function within Jupyter Lab. So within Jupyter Lab, there is the possibility to use a visual debugging tool. And I'll use it with just a small example down here. The way you start the debugger is in the top right corner. There's a little bug that you can click and enable the debugger. And then that will open a panel to the right, the debugging panel. And what this tool does is it allows you to easily and visually add breakpoints into your code, so that you can run your code until the breakpoint, and it stops, and you can see and inspect your code and the different variables, and then continue on step by step. So I'll do here, I have 2 lists with numbers, and then an empty list that is called summed list. So if I run this cell here, you can see in the top right, you might have the tree view open from beginning. Then it gets populated with our lists, 3 different lists. And if we go into the table view, we can see here are our list 1 and which type it is, and the values that are in the list. And then here I have a small for loop that will loop over the 2 lists and add them together and append that value to the summed list. And here, if I by clicking on line 2, add a breakpoint, you can see here to the right, a breakpoint popped up. So if we try to run this cell, it will start run, and then it will stop here on line 2 that is highlighted. So what we can see here on our top right, we see that we got an I variable that is a number. So that is the I in the for loop, and it has the value 0 because it's the first iteration. And then our code stopped before running this line. So what we can do now is, if on the call stack, as it's called, we can go click on the next button here. Then it will run that line and stop before running the append line. So we see here, we then created, we can make this larger. The summed value that we created from on this line appeared here in the top right and has the value 6. So 1 plus 5 from this 1 and 2 is 6. That looks all right. And then our sum list is still empty because we haven't run the last line yet. But we can then click next and see, okay, now our sum list has one more number, or it has its first number. And that way we can see, we can go step by step through this. And now we can see I has been updated to the value 1. And if we click next one more time, we can see summed value got updated to 8. The summed list is still just one value. If we run again, now it's added to that, to the summed list. Yes, so that's just a simple way to try to show you how you can kind of break up your code with this visual debugger. So, for example, if you're doing a long for loop over the index of a data frame, and in the end you see there's something wrong that's happening, this is one possible way to debug your code, and you get like this step-by-step showing of what's going on and where does it go wrong. Yeah, so in that way we can run through it, and then in this example everything worked as we wanted to. But if there was something wrong, we would see that. We could be able to see that in the top right corner in the debugging panel.
Håvard, could I ask you a question?
Yeah.
When you run this, if you are in the call stack window, if you like run that cell again, if you hit play, does it go through until it hits the breakpoint each time?
Yeah, good question. We can run through that. So if I start over and create the lists again here, now it just
I guess you need to run the other. Oh yeah, maybe it has to hit play on that one because it might be sort of in the step-by-step mode or something.
Yeah.
I'm just wondering for the lower cell, like where you have set the breakpoint, normally it would be the case that like if you click the play button, it should go, like it'll go to the breakpoint. And then if you click play, it should, I think, go through until it hits the breakpoint again and do all of the lines until it hits the breakpoint and keep kind of looping through to that point. I just was kind of curious if that's how it works here.
So I just restarted the kernel and then add the same breakpoint here, and then start running that cell. And if I click continue instead of next, then it ran the whole for loop back to here. We can see I only clicked once and it added a number to the summed list. And if I run this again by clicking continue, it will run the line 4 and then up to line 2 again. So then it, as Dave said, it will run until the next breakpoint. And in this for loop, that is like going back there. Instead of going one step and one step, it can go the whole step.
Yeah. So the reason I was just asking is because sometimes that can be helpful if you have like a longer for loop where there are multiple calculations, you might want to set more than one breakpoint. And then maybe you don't want to go every single line if there's like 50 lines between the breakpoints, but you can press play to jump, basically like to execute everything between one breakpoint to the next.
Yeah.
And in that way, this is a sort of relatively new addition to JupyterLab. And I think it's actually really could be something really useful for you students as you're learning, to be able to kind of actively monitor what the variable values are and how they change as you go through a for loop. Because it was added relatively recently, we haven't really integrated this into the teaching materials much yet. Like Håvard has just kind of done the first demonstration we've ever done with this. But I think it's quite cool, because this is one of the things that the students in the past have complained about not having, is a way to visualize what the variable values are as they're changing, for instance, in a for loop.
Yeah, and the debugging tool here gives you a much more like stepwise overview of what's happening, and also in a more visual way than what you do without the debugging tool. So yeah, as Dave said, this is the first time, so I hope it was understandable. But that was basically it for the debugging teaching this week. So I would recommend to just go through the general recommendations and read over the different parts of this notebook, as well as debugging can take very long time if you don't have any way of doing it like regularly and stepwise. So it's for you to save time in your work. Yes, I think I'll stop my screen share there, and then if I am able to, it doesn't seem so. I'll just do that. All right, and then pass it on to Dave. You are muted, Dave.
Thank you. Yeah, so thanks, Håvard. And I feel sorry that I didn't give you as much time as I might have liked for you to give the demonstrations with the assertions and with the debugging. But I hope for all of the students that are present here that you got a sense of how this works. And I think for the exercise, I just need to hide this meeting controls so I can go to the exercise, and we need to look at exercise 6, not the administrator version, but the student version of the exercise. There's a question about this week's exercise, whether we recommend the normal or light version of JupyterLab. You can use the normal Geo-Python instance for the CSC notebooks for this week's exercise. It's really only for the lesson for this week where we download a bunch of data that it can become a problem. So you can use your normal instance for this week's exercise. And yeah, what are we going to do this week? Well, exercise 6, we're going to do data analysis with Pandas once again. No surprise there, I suppose. And what we're doing is basically in 3 problems. The first 3 are all part of one notebook. We're going to analyze some climate data from the Helsinki-Vantaa airport station. So there's a data file that we have that has this data in it. So station ID, elevation, latitude, longitude, date, precipitation, average temperature, max, and min. Should look somewhat familiar, I suppose, by this point. And the overall idea, well, let's take a look here at problem number 1 through 3. It's in one notebook, again, just as a reminder. What are we going to do? Well, we're going to read in a data file. It's a little bit of a tricky data file format, so we'll read that in. Then the next step will be to convert our temperatures from Fahrenheit to Celsius, and we'll be doing this both as a conversion of the temperatures, but also a data aggregation step. So going from daily temperature values in Fahrenheit to monthly averages in Celsius. And then problem 3 is where the fun starts. So we'll come to that in just a second, what we mean there. The trickiness about the data file for problem 1 is 2 things. One, the second row has a bunch of dashes, so it's kind of like a style thing for this text file to break up visually the metadata from the data. So you have to find a way to skip over that second row. And then the no data values in this case are listed as -9999, and those should be converted to NaN. Once you've done those things to read the data file in, then you've got a set of steps here to print out a few different things, like what's the average no data, the number of no data values for the T average column, what's the number of no data values for T min, how many days do we have, when is the first observation, when's the last observation, what is the mean temperature, and then what's the mean temperature for the summer of 1969. So that's May through August of the year 1969. So you want to take a slice of data and find the average there. That's basically it for the first part. Load the data file and just do some kind of basic statistics. Step number 2 is a lot sort of heavily based, I would say, on this week's lesson, where you're going to take in a data file and you're, just going to continue with what you've used to actually create a monthly data frame, and then aggregate the values after converting them from Fahrenheit to Celsius. You'll aggregate those to be monthly average values in temp Celsius and fill those into this data frame called monthly data. So then that should mean you've got a temperature in Celsius. It's the average for that month for each month and year in the data set. Okay, that looks a lot like what we were doing in the lesson for this week. The third part is, I think, sometimes challenging, not necessarily in terms of what you have to do, but maybe understanding what you're doing. This seems to be a place where students get confused often. The idea is to calculate temperature anomalies. So we have this monthly data frame where you have a temperature that's the average for a given month and year. So January 1906, for example. We have an average temperature there. And the idea with these temperature anomalies is to see how much warmer or colder was that month, January 1906, compared to January in general, that's calculated as an average over some reference period. So what this means is that you're going to calculate in part 1, what is the average temperature for the month of January at the station we're looking at for January between 1952 and up to and including 1980. So that means that you would take the January for all of those years from 1952 to 1980 as your range of the different temperatures and calculate the mean for all of those things to give you what is a typical temperature for the month of January. Then you do the same thing for the other months, February, March, and so on. So this is kind of giving you a reference temperature. What should January's temperature normally be? And we do that by calculating over this roughly 30-year reference period. Once we have those temperatures, we can then calculate how much a given month, January for a certain year, deviated from the kind of expected or normal value. So if we took the month of January from 1906, we could compare it to what the average temperature was for January over this reference period. And it would either be warmer or colder than average based on that. And we could see how much warmer or colder was it. The idea with doing this is that we can see things like trends in how temperatures have been warming or cooling over time based on how much different they are than this kind of expected value for the reference period. To help to try to kind of explain this a little bit better, I made a new kind of diagram that I think will help. So you're going to create 2 new data frames, one for the monthly data, and the monthly data would have like a mean temperature for January 1960, mean temperature for February 1960, mean temperature for March 1960, one average temperature value for each month of each year. Then we'll have a second new data frame that gets created in this part 3 of these reference temperatures, where you have a mean temperature for the month of January over these range of years. So between 1952 and 1980, what's the average temperature for the month of January? So it'd be a single value for each month. So there'll be 12 values here total, whereas here you'll have one value for each month of each year, which means if there's like 601 values like we had in our lesson for today, there would be 601 temperatures in this monthly data frame. You're then asked to calculate what the difference is in temperature between the given month, so like January 1960, and one of the months of the reference period. So that would be the reference period of January between 1952 and 1980. So you would just take your monthly temperature value for 1960 minus the reference temperature value for January, and that will give you then this temperature anomaly, the difference in temperature. So I hope that this kind of diagram here gives you some better sense of how these different data frames relate to one another and what to do. It will take a little bit of effort to do this third part of the exercise. The first two parts I think are less challenging and very closely follow, or sorry, the first two problems, so problems 1 and 2, very closely follow the lesson materials. This is building on the lesson materials, so it does stuff that we did in the lesson, but combines it in a slightly new way. So I would say that this exercise has traditionally been one that's taken a bit more time than some of the others, and you should try to budget accordingly so you have plenty of time to make sure that you're not feeling the pressure trying to finish this close to the time when it's due. Those are the 3 problems for the week. And then we have one optional problem, number 4, if you're interested, where you can go and repeat the same steps for problems 1 through 3, but for a different data set, where you can actually go to the website, download the data, and repeat the whole set of analysis steps to calculate the temperature anomalies for the Sodankylä Lokka station. And if you're interested, that's described here, but it's an optional problem. There's not really detailed set of like rigid instructions for what to do, but rather just a list of things that you should do in order to complete this problem. And this is mostly just for your own benefit and interest. So that is exercise number 6. Are there any questions at this point? So if there aren't, I think that's it for today. Sorry, again, we've taken right up to the very end of the time and even a couple minutes past. We'll try to get the exercise or the lesson videos up sometime this afternoon. Well, actually make that this evening. And if you have questions about the exercise, we would encourage you to go to the help sessions on Thursday and Friday. You can sign up for a session and you'll find the link, I think, in the week 6 channel on Slack. So good luck with the exercise. And if you have questions, let us know in Slack or in one of the exercise help sessions. And yeah, we'll see you guys next week.